In this video, we are going to look at phase difference in simple harmonic motion. Consider three bodies, A, B, and C. Right now, we are at t equals to 0. The line E represents the equilibrium position. As you can notice, A and B are starting completely to the left, while C is starting completely to the right. All three bodies at this instant are displaced by the same amount x naught from the equilibrium position. We place an x-axis pointing to the right with its origin O at the equilibrium position. As time proceeds, all three bodies moves back and forth about the equilibrium position with amplitude x naught and time period capital T. We are going to use A as a reference to describe the motion of B and C. The motion of B is exactly as that of A, while the motion of C is always opposite to that of A. Now let us sketch the displacement from O, denoted as x, versus time t for each body. The t-axis starts at 0 and is spaced every quarter capital T, or in other words, quarter time period. The amplitude positions have also been placed at x equals to plus x naught and x equals to minus x naught. Let us denote x subscript A as a component of the displacement of body A from O in the direction of the x-axis. Similarly, we are going to denote x subscript B as a component of the displacement of body B from O in the direction of the x-axis. And finally, x subscript C is a component of the displacement of body C from O in the direction of the x-axis. At t equals to 0, we have xa equals to minus x naught, xb equals to minus x naught, and xc equals to plus x naught. At this instant, t equals to 0, all three bodies are at instantaneous rest. At t equals to capital T by 4, or quarter time period, xa is equal to 0, xb is equal to 0, and xc also is equal to 0. At this instant, all three bodies are at the equilibrium position and are moving at the same speed. However, they are not moving in the same direction. A and B are moving to the right, while C is moving to the left. At t equals to capital T by 2, or half time period, we have xa equals to plus x naught, xb equals to plus x naught, and xc equals to minus x naught. At this instant, the three bodies are at instantaneous rest. At t equals to 3/4 capital T, or 3/4 time period, we have xa equals to 0, xb equals to 0, and xc equals to 0. At this instant, all three bodies are at the equilibrium position and are moving at the same speed. But A and B are moving to the left, while C is moving to the right. Finally, at t equals to capital T, or t equals to 1 time period, xa is equal to minus x naught, xb is equal to minus x naught, and xc is equal to plus x naught. At this instant, we have completed one full oscillation. For body A and body B, the variation of the displacement from O with time is given by the equations xa equals to minus x naught cos omega t and xb equals to minus x naught cos omega t. Since we obtain the same curve for A and B, this means xa will always be equal to xb at all values of time t. So we say they are oscillating in phase. On the other hand, for body C, we obtain the displacement from O with time as xc equals to x naught cos omega t. Now let us write omega t equals to theta, where theta is simply an angle. When theta is equal to 2 pi, t is equal to capital T, then we have omega equals to 2 pi upon capital T. Omega is the angular frequency. Then we substitute this omega equal to 2 pi upon capital T into the equation omega t equals to theta, and we have 2 pi upon capital T multiplied by t equals to theta. This relation allows us to convert from time to angle and vice versa. For example, if theta is equal to pi, then t is equal to half capital T or half time period. So, an interval of time of half time period is equivalent to a angle of pi. By shifting the curves xa and xb by half time period, meaning half capital T, to the left, we obtain exactly xc. So we can say that cos omega t is equal to minus cos omega t plus pi. In other words, we are saying that cos omega t is simply a minus cos omega t, which is advanced by an amount equal to pi. Based on that, we can write xa, xb and xc as follows. xa equals to minus x naught cos omega t, xb equals to minus x naught cos omega t, and finally xc equals to minus x naught cos omega t plus pi. Now remember that the argument of a trigonometric function is called the phase, and we are going to denote it as phi. So here we have phi of A, which is simply the phase of body A, equals to omega t. Phi of B is also equal to omega t, and phi of C equals to omega t plus phi. So the phase difference between A and B, we denote it as delta phi AB, is equal to phi B minus phi A, which is equal to omega t minus omega t equals to 0. In other words, there is no phase difference between body A and body B. The phase difference between body C and body A is delta phi AC equals to phi C minus phi A, which can be written as omega t plus pi minus omega t, and this gives us pi. So the phase difference between C and A is pi, and this is clearly seen on the two graphs. So if you like the video, don't forget to share, like and subscribe. Until next time.